Welcome to the 19th lecture video for Physics 4A. We wrap up our discussion of rigid body motion including rotation by wrapping up our discussion of static equilibrium that we started last week to introduce torque. As we introduce the torque, there are some topics we skipped over because we could deal with the remainder of rotational dynamics without these finer points. So we address them in the first lecture here, including some special properties of net torque, idea of lever arm, and an illustration of situations that require the introduction of friction. We did talk about some of these out of order when we went over the rolling motion. Lever arm, in particular, is a particularly useful concept in static equilibrium analysis. So we spend additional time going over examples of lever arm finding. We have just enough time for one additional example of static equilibrium analysis in this lecture. We have many more in homework problems and the homework help videos if you are interested. And we will wrap up this lecture with a discussion of a topic that is optional for this class, Young's modulus, also known as elastic modulus. This is it for rigid body motion, until we come back to more examples of mechanics problem solving next week for mixed problem solving strategies number 2.
So we are continuing our discussion of rotation. So let me just skip a few steps that we did in the translational motion by simply referring to it. So in translational motion, after spending 2 weeks on kinematics involving position, velocity, and acceleration, and then 2D kinematics, projectile motion, how did we relate these motional quantities with the things that cause motion? What was the key relationship that we used? Isha? Yeah, force is mass times acceleration, Newton's second law. We said, net force is equal to mass times acceleration. Oops, I didn't leave room for writing down that this is Newton's second law. This is Newton's second law. And what we are now going to say is that there is a similar relationship for rotation. And we are also going to call this Newton's second law. It's the same basic law, just applying to this is the law that applies to translational case. Well, when I write down the rotational version of that, it's still the same law that simply applies to the rotational cases. So acceleration, I have a counterpart for. So I just say, so something is equal to something times angular acceleration. And what we are spending class time today is introducing and working with these two quantities that we are going to talk about. So this would be the quantity that's going to fit in here. It's analogous, in analogy with, analogous to force. And the quantity that goes in here will be analogous to, or in analogy with, mass. I'm using this as my kind of a cheat sheet because I know I'm trying to get to this relationship. And I have I know acceleration corresponds to angular acceleration, but these two are kind of new. Actually, one of them is new. We already talked about it. So something that's analogous to force, so force is what causes motion. That's what causes acceleration. And last week, we were talking about something that causes rotation, torque, right? So we already actually talked about this. So this is going to be net torque, using the symbol that we introduced last time. So this net torque is what's analogous to force. And I want to spend a little bit of time with the exercise involving net torque, or more specifically net torque first. So we went through the whole class session last time talking about how torque is related to force, right? Not just in terms of analogy, but in the sense that we wrote down this. As in, if you knew torque, so, I guess I can write it down here actually. So let me write, keep on using the same table here. So we've been using, but I won't expect that you have this memorized because you just saw it last week. So let's say if we have torque, then what else do we need to know to get the, wait. Let me draw a line here. It's actually going to go the other way. I'm not going to get started knowing the torque. I'm going to start by knowing the force. I'm going to start by knowing force, right? And what we covered the last time is, well, if you know force, then you also need to know the r, the distance. So, and there's one more unique thing that you kind of have to know. So if you look at this picture here, and let's say, let me get rid of Bob and just have Alice. So if I want to know the torque that I'm exerting on Alice, then I actually need to know two things. Two things aside from the force itself. I need to know how far the distance is that I'm applying force at. So I need to know the distance r. And the second thing I need to know is what direction I'm applying the force. If I'm applying the force radially, then there will be no torque. For maximum torque, intuitively, I would have to apply in a tangential direction, right? Yes? Yeah. So in other words, what I have to know is as I apply force, let's say, so call this R, and as I apply force, let's say I'm applying force this way, then I kind of need to know this angle here. And that's how we described torque last time. If we know force and we know this R, then the way we would write torque is given by, or eventually we're going to treat torque as a vector quantity. But for now, I'm just going to deal with the magnitude. Magnitude of torque is equal to force times the displacement, the distance r, times angle between the force and the displacement. So sine theta. That was the expression for torque, right? Yeah. So here's a bit of an exercise that I want you guys to go through, take a little bit of time going through, because this will illustrate something surprising about net torque. Something unexpected, but it sort of makes sense on the overall sense. So this is on the page 2 of your worksheet 11, problem 3. So it has these figures on the right, and for the purpose of this, the geometry is quite simple, because for all these forces, when you consider the geometry, this is the r vector, r. So all the angles are going to be 90 degrees. So sine of theta is all 1. And what I want you to do is I want you to fill out this table. So net force for A, B, C, D, direction of acceleration for all of them, net torque for A, B, C, D. Assume that the sphere has radius r, and it hopefully won't take you too long to fill this out. Please do that. And I want to point out some interesting facts. Oh, and they say find the net force about the center and the torque about the center. And if you happen to finish it early, try the additional question. That's really what I want you to point out. Who's not done with the net torque? Well, let me go through more steps. Once you get used to calculating it, it's a quick calculation, but until you do, you could, so let me go through it. So for the very first one, I'll take a little bit more time, and for the next two, I'll just write down the steps. So for A, well, you look at each of the force, and you figure out is it causing counterclockwise or clockwise torque about the center. So about the center, this is causing counterclockwise torque, and I'm going to call that positive, because that's what I'm used to. And this is clockwise torque, and I'm going to call that negative. What about the force 3F? Is it causing any torque? Not about the center. So, all right. So now what I'm going to write down is force times the distance for each one of them. So very first force will be plus Fr, right? The plus for the counterclockwise direction, and here the distance is r. The second force, it's at the distance of r over 2, so it'll be plus Fr minus 2F, oops, times r over 2. Sorry, what was the question?
I suggest that Fr2 is going to cancel.
Yeah. So it adds up to 0. A lot of them are zeros, but not all of them are zeros. Good? So, so that's the procedure you're going through. So let me do that for B, C, and D. For B, it's these two forces that's causing torque. So it'll be minus Fr, plus Fr, that's equal to 0. For the picture C, it's once again these two forces that are causing torque. So minus Fr plus Fr equal to 0. It's the same thing, isn't it? But it's important that you do step by step because of the last thing we're going to do. D, so small force F doesn't cause any torque. Big force F, this causes counterclockwise torque. This causes counterclockwise again. So it'll be Fr plus 2Fr. So total of 3Fr of torque. Good? Yes? All right, so you might say direction of angular acceleration, not relevant for all these that have 0 torque. Here it's going to be counterclockwise. Good? The answers make sense? Now, in terms of filling out table, this is not terribly interesting work. But there's a reason I wanted you to have this table. Because what we are now going to try is the additional question where we are going to shift to the center of rotation. Instead of torque about the center, we are going to find the torque about the bottom of the disk. And I will give you, well, there's really 3 examples I want you to do. So A and B, that's what's here. Try doing it for A and B. So once again, shift to the center so that now center is here at the bottom. Do that for A and do that for B. And see what you get. And if you have time, do that also for D. So what I'm going to ask you after you have done A and B is what makes the difference. And D will be a way to confirm what your guess was for what makes the difference. Everyone done with all the network calculation? OK, so this is for A. So I'm trying to do them in order from, let's say, top to bottom. So force F, let me erase these marks. I can't read anything with those marks. So force F times the distance. Here it's 2r because it's from the bottom to the top, right? Counterclockwise, so it's positive. The second force, 3F, this time it's not producing 0 torque. It's producing clockwise torque, so minus force 3F times the distance r. The last force, its direction has changed. About the center, we used to describe it as clockwise, but about the bottom, it's now counterclockwise. So it's it's plus 2F times the distance r over 2. And they somehow mysteriously adds up to 0, which is the same answer we had before. So you might think, all right, so if it's 0, is it always 0? And if you're thinking that, that's when you get corrected in B, right? Because when you finish B, this is what you get. minus F2R minus 2FR, and then 0 for the force that's applying right at the bottom. So, well, it's not 0. It's a minus 4FR. So, all right, that's a bit mysterious. So, why does it, if you had to guess, why is it that net torque in one case somehow doesn't depend on where you put the center? It's a 0 in both cases, but net torque in the other case does seem to depend on where you put the center. It's a 0 in one, but not 0 in the other. Any guesses?
Because the force at the middle is
Yeah, I'm not looking for specifics. I'm looking for a general rule that can always tell me if I'll get a situation like A, meaning I don't have to worry about where the center is. Net torque will be somehow unchanging wherever the center is. Or it's like B, where I have to worry about it. Asia, is that what you're going to say? Okay, yeah. So what Edward and Asia were saying is net force. That's the thing that seems to make a difference. In A, the net force was 0. In B, well, it wasn't 0. So at least that's a good guess. So let me test that with D, where you can do it with C also, but D is more interesting. Because in D, you have a non-zero net torque. And if our rule, the general condition is that whenever net force is equal to 0, net torque will be somehow independent of where the center is. It should be the case. Let's try it. So net torque for D is counterclockwise plus F times 2R, and then clockwise, it's counterclockwise again. So plus F times R. And then the bottom force doesn't produce any torque. So all of this is equal to plus 3FR, which is the same value that we calculated before. And I will give this to you as a general rule. So as a general rule, whenever net force is equal to 0, what that means is it implies that net torque is independent of I guess, should I say axis? Yeah, independent of axis. So independent of where you calculate each individual torque from. Somehow they will all combine to give you the same torque that you got before, same net torque that you got before. It's something useful to know, especially when you're doing static equilibrium questions, because this is one of the conditions that have to hold for static equilibrium, right? So what that means in static equilibrium questions, you can actually pick the center of rotation as it's convenient for you. And in fact, that's what I've been doing in the few static equilibrium problems we have done in class last week, and I guess today not really, but I have been picking the center of rotation sort of as it fits my fancy. And what this is telling you is that, yeah, you can do that. You don't have to worry about your net torque suddenly changing if you change your center of rotation, as long as this is true. So that means if you're dealing with the dynamics case, that's when it might actually matter where your center of rotation is. And when we come to those problems, I'll point out some general rules for a correct center of rotation, or a center of rotation that will give you a meaningful result. Okay, question?
Why do we use R over 2 for A?
Because, well, A is the only one where the force is acting is at a distance of R over 2 from one of the centers, and also distance of R over 2 from the other center. In all the other figures, there's no force like that. Just case is specific. Question? Yeah?
Yes. So for A, why do we use 2R instead?
2R. It's because, so this is for where the net torque was about the bottom of the disk. So for this particular calculation, I want you to remember the setup. We were saying, okay, we are not calculating the torque about the center of the disk. We are calculating it about the bottom of the disk. Yeah, and the distance in this case is now 2r. Yeah. So for individual torque calculations, you still have to worry about, where is the center. You still have to pay attention to that. But so what this is telling you is that you can pick your center of rotation in a way it's convenient for you if net force is equal to 0. If net force is not equal to 0, then usually there will be something that tells you what the center of rotation has to be. You have to go with it. You don't really have a choice. Got questions, comments? All right. So I want to talk about one more thing about torque before I go into a long, well, not long, I don't have the time, go into some discussion of rotational inertia. So it has to do with sort of a way to look at torque. So let me write down this torque that I wrote here in 3 different ways. I won't really explain why yet, but let me just write that down. Everyone can see the board where torque is written, yes? I'm going to write this in, well, let me leave this as a generic expression and write it in 2 different ways. I'm going to write this as F sine theta times R, or if it strikes my fancy, I'll say it's F times R sine theta, but with this parenthesis, particular. Both of these ways represent a particular way of describing the torque. So you could take this as the general formula for the magnitude of torque. Well, here's 2 different ways of interpreting it. Let's say you had, this is a result of a force that points in a particular direction, acting at a point where R vector works out this way. I'm going to just, this could be the actual R vector, right? But I'm going to imagine translating it over so that I draw my R this way. Okay? And what this formula is saying is, the magnitude is magnitude of F times magnitude of R times the sine of the angle between them. Right? That's sort of the neutral version where you are not taking any particular geometric interpretation. But here's a way you can take a geometric interpretation in both of these cases. You could say, you could take this view. So what this is you're saying, well, I want to take a component of force. And what this F sine theta is, it's this component of force. This is my F sine theta. You can see it in the geometry here, right? Or I could call this the perpendicular component of force. So perpendicular component of force times the displacement R. That's one way of looking at it. And there are problems where it's convenient to look at it that way. You'll see that in homework. But you can also insist that, well, that's not the only way to look at it. There's a second way to look at it. It's to say, well, I'm going to leave the force alone, and I'm going to look at the perpendicular component of the displacement. So instead of taking this view, I'm going to say, well, let's take a component of R that's perpendicular to this line. So this R, this component here. So this would be the perpendicular component of R. And in terms of that, this would be the force times R perpendicular. And if I had to pick between these 2 different interpretations, I will tell you that this is more commonly useful. And that's why this actually gets its own name. This is called lever arm. The perpendicular component of displacement that matters for rotation, it's called the lever arm. It gets its own name because it's useful that often. And the best demonstration I have for that is this thing that I keep kicking around down here. So it's a spool, right? And I will show you 2, one kind of expected way this moves, and two different ways where it moves in an unexpected way. So, I'm not doing a magic trick, but it's nothing special. It's just a spool with a wire wrapped around it. So right now it's wrapped around from the top. If I pull it to your left, which direction do you think this spool will roll? Like I'm gonna pull, which direction should it roll? Counterclockwise or clockwise? Counterclockwise, right? All right, good. That's the expected one. Let me do the first of the unexpected motion. So I'm going to take this spool and I'm going to pull it. So this time the string comes from the bottom. Which way do you expect it to roll? Clockwise or counterclockwise? A lot of people think it'll roll clockwise. Let me try it. Both counterclockwise. And it almost makes sense. This is so using the contact points as the center of rotation, what is the direction of the torque due to this pull? Counterclockwise, right? Yeah, so this is rolling in a way that's consistent with the counterclockwise rotation. Now, the reason a lot of you had the intuition for clockwise rotation is that you are actually imagining this. You are imagining this as being supported in the center. Then as I pull this out, it'll be clockwise rotation, right? So, when we are looking at it in a static equilibrium sense, those two descriptions somehow must agree. That when I use this bottom as the center of rotation, which easily gives a counterclockwise rotation, that has to agree with when I pick the actual center as the center of rotation. So what are we forgetting that many of you are missing? That this has to end up having net counterclockwise net torque. What are you missing here in your consideration? Let me give you one hint. It must be some kind of force that you are forgetting. So, you are considering this tension. You are saying, okay, this tension force is giving clockwise rotation. That's why many of you said clockwise. But I'm telling you that you guys are forgetting one particular force, which is giving you counterclockwise torque with this as the center and resulting in net counterclockwise rotation.
Friction?
Yeah, it's friction. Yeah. So, gravity and normal force, they do nothing. They act on the, more or less the center. There's no torque due to gravity or normal force. So it's friction that, there's a friction. As I pull it to the left, there's a friction acting to the right. And it's that friction force that's providing counterclockwise torque. And I guess because it's at the greater radius, it's generating greater torque with a smaller amount of force. So that the net result is that it rolls counterclockwise. Yeah? So I think I've mentioned this class several times. We try to ignore friction except when we can't. This is one of those cases where except when you can't. When someone describes something rolling without slipping, that will always involve friction even when the problem doesn't explicitly mention it. Yeah? Okay, let me give you one more type of pull, and I have to do this kind of carefully. As you watch me pull, what would you guess the net torque on this spool is? Yeah, it's not rotating at all, right? I'm pulling in a very particular kind of way, designed to give it a zero torque. So let's use the bottom as my center of rotation. That'll make the consideration much simpler because I don't have to worry about friction. However much friction is there, I don't want to have to worry about it. So what do you notice about the direction I'm pulling with the tension? That I am somehow giving the spool zero net torque. Radius coming from this point, right? So if you take this tension line, it looks as though it's going straight to this point. Okay? So here, I'm pulling this in a way designed to make a lever arm equal to zero. So this particular demo is illustrating the usefulness of the lever arm concept. Because if you're trying to do this calculation, then it takes maybe more geometric effort. But lever arm is a way of describing a particular type of geometry that's useful in figuring out the torque. I probably should, in a future class, we'll work on some problems that where I can describe to you the procedure for identifying this lever arm. I mean, you can do it in a way that feels comfortable to you. It's, as long as this is the component of the R vector that's perpendicular to the force, then however you do it is the correct way to do it. But there's a particular procedure you can follow that will make things maybe easier. I will cover some problem in a future class where I can demonstrate that procedure. Yeah?
So for the calculation of lever arm, what I have done is I picked out a number of figures from the textbook so that I can illustrate lever arm. There's quite a few of them, and I think I can go through all of them. It's not very long to go over them, so might as well. So this first figure is what in the textbook to introduce torque, and I guess the place I should start from is sort of the locating lever arm in the formula for torque. So this is what you have seen as the formula for torque. So in the textbook and elsewhere, you see the definition of torque as displacement R cross product with the force vector. And we've talked about this cross product, and so this is the full description of torque, especially in this vector sense. And you've seen before exam 2 how this vector property of torque is important in explaining something like a precession. Now, most of the time when we deal with the torque, we don't need to deal with the full three-dimensional vector aspect. Really what we are more interested in is the magnitude of torque. And formula for that becomes a little bit simpler. It's the magnitude of the displacement, or just the distance, times the magnitude of the force, times sine theta. So you could take the description of torque as this. Then the question I want to address is where in this formula do you locate the lever arm? And for that, I would like to rewrite this formula in two different ways. I guess one of the ways I actually don't need to do any rewriting. I can just put this parenthesis here to make the grouping clear. The rewriting I might have to do is to move this sine theta around a little bit to say r sine theta times f. And to make the grouping clear, I might put parentheses around r sine theta. And this is two different ways of writing this one and the same formula. And in each of these ways, the quantity that I put under the parenthesis, you can give that a meaning. So just to avoid any confusion, this theta, it refers to the angle between the displacement vector and the force vector. So to point out the theta in these figures here, in example A, so this is the direction for force. So the theta would be this angle here. This would be theta. A, B, C, they are all the same. Theta would be this angle here because I'm imagining this being the F and this being R. So with these two vectors, what we define as theta is the angle between these two vectors. And you can see this here. Here's F. And I guess something that's a little bit confusing at times is, so if this is R, then it's natural to say, all right, so putting those two vectors at the same origin, this is my R vector, then shouldn't this be theta? You can, well, mathematically, there's no big distinction between the two. Since whether you label this acute angle as theta or this obtuse angle as theta, the way we are using this angle is as sine of theta. And sine of, it comes down to sine of theta is equal to sine of 180 degree minus theta. So, so whether you identify identify theta as this obtuse angle, which from my view is the correct identification for theta, or whether you use this angle theta, they both end up giving you the same answer. So with that identification of theta, what I want to say is that this quantity here, you can identify this as the perpendicular component of displacement. In fact, that is exactly what is done here. So, and this is what we are calling lever arm. And this is the more useful way to calculate torque. That's okay. This is the way to calculate torque that is more useful in more situations. This is a perfectly valid way to do it. And this particular expression would represent the perpendicular component of the force. So when you are calculating torque, you could do it as a distance times the perpendicular component of the torque, or you could do it instead as force times the perpendicular component of displacement. And both are valid, both give you the same answer. But graphically, you will find that there are more situations where lever arm gives a more intuitive answer. Um, so, so yeah, let me uh, let me describe and demonstrate the procedure for identifying lever arm in a figure in the examples below. I could use this figure here to explain the procedure, but well, should I? Yeah, I think I should. So let me do that. Let me use this figure D to explain the procedure for finding lever arm in the figure. So so this is the procedure. What you are, so I described the lever arm as the perpendicular distance. So what the procedure is designed to do is find that perpendicular distance. So when we say perpendicular distance, this is distance between what and what. And what I would say is it's the distance between your center of rotation, which will either be obvious as what that is, or you define it yourself. Here, the hinge is a natural choice for the center of rotation. So it's the distance between the center of rotation and what I like to call line of force. I think a more common phrase for this is line of force or line of action. I think I still prefer line of force because action such an ambiguous term in physics. I don't like using the word action. So I'm just going to call it line of force. But whatever the word you use, it's the line that you associate with the force that whose torque that you're trying to calculate. Um, and when you're drawing free body diagram for rigid body motion, you have to be careful at which point of the rigid body the force is acting. So the force is acting on this point. If I'm drawing a proper free body diagram, I would probably label it like this, with the force appearing to come from the point where you are applying it. And you're trying to find the distance between this point and the line of force. So this is where you have to be careful. so I am not talking about this distance here, because that distance would be just r, and I'm not looking for that. I'm looking for something that's almost like in the, I don't know if you remember learning this in geometry. In geometry, you talk about a distance between a line, a geometric object line, and a point. And when you want to measure the distance, you measure the distance using a perpendicular line segment, or segment that's perpendicular to the line. So that's what we are going to do here. This force, unfortunately, is only a segment. So we need to do first, as a matter of procedure, extend this segment into a line that goes infinitely in either direction, and find the perpendicular segment that drops down from the point onto that line of force. And this is the lever arm. So let me illustrate this procedure with a few more figures, because practice makes perfect, and there's a benefit to seeing this procedure in multiple contexts, in multiple different figures. So I have some figures here just copied out of examples in the textbook. So let me just go through this and illustrate my procedure here for finding the lever arm. So here, this is what I'm going to do. I'm going to start by extending this force vector into a line. So what's important here is that the line goes through the point at which the force is acting, and it has the same orientation as the force. Then looking at here, this is the axis of rotation. This is the perpendicular segment, and I would call this the lever arm, or perpendicular distance from the axis of rotation to the line of force. All right, let's keep going through a few more examples. Now, example like this one is where it might feel more natural to use the other description of torque. Just to spell it out, let me say that. So the other description of torque was the distance times the perpendicular component of force. And here, it's very natural to do that. It's very natural to take this force, break it up into two components, one that's perpendicular to R, and one that's going to be parallel to R. So this is the parallel component, this is the perpendicular component, and take this to calculate the torque. So the component that contributes to torque would look like this. It's very natural to do that, and nothing wrong with that if you do that. So this is probably one of those situations where you would just use this formula and not bother finding lever arm. But I could ask you, find the lever arm. And if I were to do that, then this is how you would do it. Let me demonstrate the procedure. You first start by extending the force vector into a line. So let me try to do that as straightly as I can. So here's an extension of that force vector into a line. And what we do is, all right, here's the point, the axis of rotation, and you drop down perpendicular segment. And this perpendicular segment is my lever arm. And you can see that it is the same angle theta that you are dealing with. So this is the same angle theta that you had before, and this perpendicular segment is r sine 30 degrees. So in the final answer, whether you use perpendicular component of r or the perpendicular component of f1, it doesn't change your final answer. What it does change is how you represent it on a figure. All right, let's see. I think I have a few more examples. Oh, yeah. So these are, I think the examples up to this were from chapter 10, back when we were doing rigid body motion. And these examples are now from chapter 12. And, they don't all have to be complicated. here is a very simple example where basically my lever arm is, well, what you see here. This is the lever arm for W. This is the lever arm for W2. This is the lever arm for W3. And, you do want to kind of account for the sense of rotation separately for each one. But, they are all 90 degrees here. They don't have to be very complicated. The lever arm is the actual displacement. Now, the wonderful thing about static equilibrium situations we cover in chapter 12 is that sometimes they can get very complicated. So this is one of those examples. It's examples of a biomechanical motion that is relatively simple to describe. You're describing a motion where someone's lifting a ball, but there's a lot of force involved here. There's a force that's acting on the joint, which provides net force but no net torque. There's a force acting on this point of attachment by the muscle, which provides net force and torque. There's a force, I guess here the ball is being pulled down by gravity, and when you look at the force on the hand is being pushed down through the normal force. So it's a very complicated picture. When you look at the free body diagram that's in the example, that reflects that. It's showing you the diagram with three forces at three locations. And you can see here that your textbook has taken the other option. It has taken the option to calculate the torque as the displacement times the perpendicular component of the force, because it chose the axis along the direction of displacement and broke all the forces down into components that's parallel and components that are perpendicular. So after having done all this work, it's probably simplest to use this as the perpendicular component of the force and use that to help you finish the calculation. That's perfectly valid. So let me use this example to illustrate if you are going the other way, instead of using the perpendicular component of force. If you are instead using the perpendicular component of the displacement, that is the lever arm, how you would have done this analysis differently. For one, I don't know if I can hide them. Okay, so for one, you don't be doing any of this breaking down forces into components. So let me get rid of these very confusing arrows. And you do deal with the force as one whole vector. You have, so for example, you have the one whole vector here. But that particular force is going to result in zero torque, so let me not deal with that. Let me deal instead with this kind of a tension force from the muscle. So what you do, this is the procedure. You extend this force into a line so that you have a graphical representation of the line of force. And what you do is you drop down a perpendicular segment from the center of rotation onto that line. So this is what you would say the lever arm for tension force T. Okay? Let's continue. So I have this W, or this is the kind of the weight of the ball. So to find the torque due to this force, I do the same thing. Extend this force into a line for line of force, and then you drop down a perpendicular segment from the center of rotation all the way down to that line. And this entire distance here is the perpendicular component of the um, perpendicular component of the displacement to the point at which the weight force or something related to that is acting. Good. I think I have one more example remaining. Oh, actually two. I have one more example from chapter 12 here. This one, I think you've actually seen me do some work with it in one of the recorded videos that, oh, okay, I guess I posted today, so maybe you haven't seen it yet. So when you analyze this ladder on wall situation, this is the free body diagram you end up drawing. And the process for drawing this is very interesting. I encourage you to watch the lecture video where I do the ladder on wall or carpenter on ladder analysis. So here, I can use the procedure I described to calculate the torque due to each one of these four forces. Now, even though I can do it for all four forces, let me just stop and recognize that the normal force and the friction force here, they are both going to result in torque of 0 because they are right on the point of acting right on the point of rotation. So the lever arm for both either of them is going to be 0. So, all right, let's not waste too much time there. So let's look at instead then lever arm for W or the weight of the ladder. So same procedure. I start by extending this force into a line. Then starting from this point of rotation here, I find the perpendicular segment that drops down to that line. This is the perpendicular segment, and the length of this segment is the lever arm for the weight force. Good? Now, what makes things interesting here is that this normal force from the wall is going in a different direction because it's normal force from a vertical wall. So, but the procedure remains the same. I start by extending this force into a line. So here that line looks horizontal because it's going in the same direction that the force is. And starting from this point here, I drop a perpendicular segment down to this line. So when I drop that perpendicular segment, it has to look this way. So this is the lever arm for the normal force. Um, Normal force, I guess I would call it F. Normal force F. And you can see that using this angle beta between the force and the displacement, that this lever arm is given by the formula you would expect, R sine beta times F. But what this method of identifying lever arm graphically is useful is when you're trying to develop some intuition for a situation. I think I have just one more figure. Oh, this one. I forget if this comes from chapter 10 or 12. But I guess here it's a bit of an odd situation because you have to. I think you have to imagine this being drawn on a kind of three-dimensional system. So I could call this x-axis, and let's say G is perpendicular upward out of the surface. Then y-axis should look something like this. Oh, I guess those plane edges are kind of parallel to the axis. So x, y, z. That's sort of how it appears. So here, I guess once again, it's kind of nicer to break down forces into the parallel and the perpendicular component. And it's perfectly fine to do that. But let me just use this to illustrate what the lever arm looks like. As before, you extend the force into a line of force. And from this origin, I try to drop down perpendicular direction. And I hope I'm drawing this right. I hope in the perspective view this makes sense. So this appears perpendicular, and this is my lever arm. And similar here, I extend this force vector into a line. then I can see, starting from this axis of rotation, I can drop down a perpendicular line segment here. Okay, okay, I think that's kind of all the illustrations of locating lever arm. Now, the wonderful thing about standard strategy is almost regardless of what it asks, the series of steps that you would go through doesn't change. That's the kind of whole point of a standard strategy, that it's a fixed set of steps that you can apply almost no matter what your complicated situation problem is. So here, let me just highlight some of the information that I'll probably end up needing. So this whole scaffold, it has mass of 50 kilograms. Let me call that M1. Mass of M1. Oh, and given the length, call that L by 2 light cables. So light is code word for massless. 58 kilogram painter. So let me call that M2. Stands 1 meter. So let me call that L2. From the left hand of the scaffold, and its paint bucket is 1.5 meter from the right end. Let me call this L3. If the tension in the left cable, let's call that TL, is twice that in the right cable, call that TR. Find the tensions in the cables and the mass of the bucket. Express all answers rounded to 1. Okay. So it's a quite complicated scenario, and it's a complicated scenario like this where standard strategy excels, because you handle one chunk at a time that you can handle. The very first chunk is standard strategy step number 1, free body diagram. So I'm going to draw a separate free body diagram here. At each step, making sure that I didn't forget a force. So this is the scaffold that I will need. So I got the mass of the scaffold from which I can get gravitational force on the scaffold, M1G. And I have the painter who's going to be applying a normal force on the scaffold equal to M2G. Oh, and I guess I don't know the mass of the bucket. So that I don't have to spell out bucket each time, let me call this MB. So the bucket, at the location of the bucket, there will be downward, again, normal force, MBG on the scaffold. So those are all downward forces. I need some upward forces. In this problem, it looks like there are 2 upward forces here provided by the tension. So let me call that TL and TR. Now, kind of looking at this picture and thinking through it, it looks like I will probably need to use both the set of equilibrium condition equations. So remember, at static equilibrium, the equilibrium condition you have is that net force is equal to 0 and net torque is equal to 0. And in the previous question, I could make the first equation irrelevant by kind of not preventing torque from depending on a particular unknown force. Now here I have 2 unknown forces, tension on the left and tension on the right. I can get rid of effect of one force by putting the origin right at where one of the forces are acting, but the other force will still continue to generate torque. So I'm gonna need to write down both of the equilibrium condition equations, 1 and 2. So, all right, step number 2, I need to define coordinate axis. In a problem like this, comes down to choosing a center of rotation. I guess I'll choose this as my center of rotation. I already marked it. All right, then I guess that's it. So all the forces are in the vertical direction, so I don't need to decompose anything. Now I'm ready to write down Newton's second law equations. That is net force. Here, this time I need to carefully write down all the forces. The upward forces first, TL plus TR, and then the downward forces, minus M1G, minus M2G, minus MBG. And because it's a static equilibrium, all of this should add up to 0. Let's write down the net torque. That's gonna take a bit of space. The tension, the left tension generates no torque because the lever arm there is 0. The right tension, it looks like the lever arm there is L, the entire length of the scaffold. So, I need to decide on a sign convention. Here, let me use the other convention. So I'll say counterclockwise is positive and that clockwise is negative. This actually matches the usual angle convention better, where you say if something is moving from the positive axis upward, which is counterclockwise, that's a positive angle. But the main thing necessary here is consistency. So let's write it down. The lever arm is L, so the sign is plus, right? What we decided just now. The lever arm is L times the force, TR. Oops, why am I? I don't know why I'm spending the TR. Once again, this is the definition of torque we are using. The torque is lever arm times force. And I'm handling the direction of torque separately with the signs that I add. Okay, all the rest of the forces are clockwise about this point. So they are all going to get a negative sign. Let's just write them down, matching pair at a time. So minus, M1 is acting at the center of the scaffold, so the lever arm should be L over 2 times the force, M1G, minus M2G, the distance we were given as L2 earlier, L2 M2G, minus, now this one we need to figure out. We are given L3, but that's not the distance from the center of rotation. The distance from the center of rotation is this, which should be L minus L3. So L minus L3, M bucket G. And that should add up to 0. All right. So let's just do a quick check. This is the check that you want to do at the end of the final step in the standard strategy. You want to make sure that you have enough equations. So you have the tension forces, which are unknown. You are given the masses, M1 and 2. You are not given the mass of the bucket. So you have three unknowns, but only 2 equations, which means we need more information. Here it is. It says if the tension in the left cable is twice that in the right cable. So that's giving us some information. The way to make use of any information in a physics problem is see if you can express that in terms of equation. So tension in the left cable, TL, is twice the tension in the right cable. So that's equal to 2R. All right, so now we have equations 1, 2, and 3 without introducing any new unknowns. So we are good to go. We have 3 equations, 3 unknowns. This is solvable. Let me try to solve it quickly. Okay, so this is going to be my strategy. It looks like we already don't have TL in the second equation. So what I can do is I can use equation 3 to eliminate TL from equation 1. Let me do that. Then what you end up with is 0 is equal to TL, in terms of TR, that's 2TR plus TR. So let me write that as 3TR, kind of simplifying as I go. Minus, let me factor out G. So it's M1 plus M2 plus MB G. Okay, that's equation 1. And equation 2 doesn't change quite yet. And I guess we'll just go systematically. We have, so between equation 2 and equation 4, we have two equations and two unknowns, TR and MB. So the thing to do is a substitution. I think the easiest thing is to solve equation 4 for TR, plug it in into equation 2, see what we get, and solve that for MB. So let's, so solving this for TR, what you get is TR is equal to sum of the masses divided by 3 times G. So let me plug that in into equation 2 to get 0 is equal to, first 0 I don't need to write, L over 3 times M1 plus M2 plus MB G. Can I, let me just write it out. So minus, let me, parenthesis, L2 over M1 plus M2 and plus, let me just expand this out, L MB minus L3 MB G. And I hope you see that as you stare at this expression, we can, oops, I forgot something there. There should have been L2 in front of M2. I was checking the units and it didn't work out, that's why. Okay. All right, so some things cancel out from the get-go. G's cancel out, good, we don't have to deal with that. And I guess we need to solve this for MB. So let me collect the like terms. Collecting the like terms, this is what I get. 0 is equal to, I'm just going to collect all the terms with the MB in it. So it's L over 3 minus L MB. So collecting those two, I have minus 2/3 L MB. So I guess I'll just write down the rest. Wait, I forgot the L3 MB. So it should be minus 2/3 L plus L3 MB. Okay, now we can collect the rest of the terms. So we have, so plus, I guess I'll just do it one by one. So I have L over 3 M1 minus L over 2 M1. I happen to know that fraction algebra arithmetic in my head. It's minus L over 6 M1. Then I have M2 is going to be a bit of a mix. So I have plus L over 3 minus L2 M2. I already did all the MBs, so I think we are done there. Okay, I guess I just solve for MB. So I have all these terms on the right, move them over, divide up by this factor here, and then we'll be done. I guess this is the point at which I might just plug in the numbers, because I don't really see any algebraic simplifications coming up. So yeah, from this point on, the symbols you track isn't really worthwhile. So let me just write out what those quantities are in numerical terms. So minus 3.167 meters. Okay, let's combine the other term. So I have 19 meter kilogram. All right, so to solve for MB, I imagine moving this term over to the left-hand side, and and then divide up by divide out by 3.167, which is no longer negative, then I should get a positive answer. So the positive answer is MB is equal to, I guess 6.0. 6.0 kilogram. Let's plug in the numbers and see. Maybe I could have kept a symbol again. Some things will have canceled out. 6 kilograms. I have two more parts. Well, the other two parts, I'll leave that for you. Once you have the mass, then the rest is kind of working your way backward, because then you have this expression for TR, where the only unknown is MB that you can plug in from before. And once you have TR, then you have TL through this expression here. The rest are kind of just wrapping things up once you get the first part correct, and the rest are more guaranteed. And I think it's worth talking about. Young's modulus is something that one of my favorite labs in my version of Physics 4A when I took it at Cerritos College many years ago. One of my favorite labs actually dealt with the Young's modulus. It had this big setup with really heavy masses being held by steel cable, I think. And so as you hang more mass, the steel cable extends a little bit. And using that, you can measure Young's modulus of steel, whatever the cable is made out of. And as you make a careful measurement, you can also measure something called the hysteresis. And I really like that lab. It would be nice to have something similar for our class. Now, one thing is the way we cover our topics, we skip this, and which is totally standard. I used to be GSI at UC Berkeley, and they skip Young's modulus more or less too. And it's not concept-wise, it's not difficult. And for those who might go on to be engineers, especially civil engineers, it's a particularly important topic: how materials deform under stress and force. So I just want you to highlight some things and point out some things. You can read it through the section if you want. That's true of any skipped topics. The textbook is there really to provide a comprehensive basis so that you don't have to rely on me covering everything that might be important. They are in the textbook. So I guess we can start out with some definition of what they call stress, and they should be defining strain. Stress in the simplest sense is kind of simple. It's like pressure, force per area. That's it. That's a stress. We talked about force per area when we were discussing fluids, which your textbook will do in the next chapter. Stress and pressure have the same unit, and they are similar in certain ways. Bulk stress is probably the closest to what you think of as pressure. I mean, even this description, submarine in depths of ocean, yeah, that is exactly pressure. So stress in many ways is similar to pressure. With the tensile stress, it's a little bit different in that you are pulling things apart rather than pressing. But shear stress is a little bit more different because it's sliding kind of. There's a kind of a saying that you might hear in an upper division mechanics, which is that stress is a tensor. What is a tensor? And all that's meant to say is that stress is something that's mathematically more complicated object than a scalar, which is just a number, than a vector, which is just like a row vector, column vector or row vector. Stress is a matrix. So to fully characterize any general kind of stress under any conditions, you don't need a whole matrix of stuff. But your textbook talks about it in terms of tensile bulk stress. A bulk stress would be the diagonal elements of the matrix, and in order to include the shear stress in your mathematics, that's where you need the off diagonal elements. Anyways, but in the basic terms, we can think of stress as being like pressure. And strain, which is the second quantity that's necessary to describe Young's modulus, is the amount of deformation. I think it's defined as change in length per actual length, so like a fractional change in length. I swear I wasn't reading it. Fractional change in either length or volume. So strain is a unitless quantity. Stress has a unit of pressure, and strain by its design is a unitless quantity that tells you by what fraction it's changing. So, um, so this is something that comes from an observation that uh, as things are being stressed, either being pulled, pushed, or shear, usually either being pulled or pushed. I think of being pulled is an easier one to consider because then you don't have to worry about materials moving out of way. So as you pull something, as you apply a tensile stress, if you observe any material, so you know something like these strings, they so to the very first degree, you might say, oh, as you pull, it doesn't change its length. That's where we describe tension force and that sort of stuff. But so that's the roughest level description. That's mostly correct. But as you observe it very carefully, if you tie down one end and you kind of see as you apply more and more force how much the other end changes, you might notice that it actually does move. So as you apply stress, there is strain. There is change in the length, and it's a very small amount for most materials. And for something weak like this string, if you pulled hard enough, eventually it would break. Now, before it breaks, where it's stretching out a little bit, and when you release the stress, then it's not as stretched out. That's where we describe something called elastic modulus, or I learned it by the name Young's modulus, and it's used to characterize materials. And the rest of so Young's modulus, looking at this equation, it would be defined as stress per strain. So a material that has a very small Young's modulus, it indicates stress over strain. So strain would be large for relatively small stress. So material with a small Young's modulus is materials that stretch easily. Like your spring is actually, you could describe a spring with a Young's modulus, except I guess by convention we use Young's modulus to describe material properties, and springs are made up of coil of thing, and the how much it stretches, that's not a material property, that's the object property. So but Young's modulus is the same idea except at a material level. So you apply some stress, and then there's a restoring force that's like a Hooke's law force. It pulls it back, and the amount of stress that's needed to stretch it is proportional to the strain. So this can be used to characterize different materials. And so you can see here, so materials that you think of as being strong, like a steel, you can see that has a fairly large Young's modulus. And materials that are weak, like wood, even hardwood, it has smaller Young's modulus. And it's on this table where you can describe different properties of like even metal. So it has several different metals: steel, nickel, iron, all kind of a similar Young's modulus. They are hard materials. And when you go to aluminum, it has smaller Young's modulus. So when you're like building a structure or building an apparatus, then you do have to think about, if you build it out of aluminum, in addition to all the other things, well, it's gonna deform more easily than iron would. It's just a part of the material property. So yeah, and I guess that's maybe all that's there to cover. And that's kind of the reason we skip, and go through the rest of the textbook section, read the descriptions. And as I was preparing for this meeting, one thing kind of confused me, because I had this memory that bulk modulus ought to be 3 times the Young's modulus. And when you look at this table, that's not the case. So I'm misremembering something. As you can see in this table, bulk modulus is pretty close to Young's modulus. So whether you are looking at the volume change as a fraction, as a function of the bulk stress, or if you're looking at the change in the length with the tensile stress, for the same material, that kind of changes not all that significantly different. Shear modulus is a different beast altogether, so I won't try to address it. This is sort of the thing that we do when we say, oh, stress is a tensor. And what I mean is, we don't want to really talk about it. Leave that up for an upper division, graduate level classes, for your engineering classes. So why did I think that bulk modulus should be, there's some factor of 3 difference between the two? And I looked around a little bit and finally figured out what I was confusing it with, which technically isn't part of this semester, but it's something that a lot of you will see in the next semester. So might as well bring it up. It has to do with the thermal expansion. And there's a mathematical reason for what I'm about to show you. So let me just get to that. Thermal expansion. So with the thermal expansion, there's something called coefficient of expansion. It's kind of in some basic conceptual level similar to how we define Young's modulus. It's a phenomenological thing. So, with the Young's modulus, you observe that as you apply force, there's a little bit of a deformation. So you do the experiment, measure it, and characterize it. A phenomenological description means something that's experimentally based, as opposed to like a theoretical explanation or anyways. Coefficient of thermal expansion is something similar. You get a material and you observe that when its temperature changes, its length changes a little bit. In fact, this phenomenon is basis of many of our thermometers. And this change can be characterized. Again, it's an experimental thing. So you can measure the change of temperature, see how much length has changed, and you get to an expression that looks like this. Amount of change in length, turns out, yeah, it's proportional to length, kind of like with a strain. So there's something that looks like a strain here as well. And amount of strain, although I guess we don't call it that because it's outside of the context of Young's modulus. So amount of strain here is proportional to temperature. So when you come up with the coefficient of expansion, it'll be something per Kelvin per degree C. And this alpha is the coefficient of linear expansion, how much is something expands in one dimension, one of the 3 dimensions. And this is the table for coefficient of linear expansion. And when you look through it, it's interesting to look through. Aluminum has that. There are some. Iron also has a smaller coefficient of expansion. So I guess that's great. Really, Invar, I thought it could be even smaller. And there are some materials with there should be some materials with a negative coefficient of expansion. Not sure. Well, doesn't matter. But okay, so as you look at this table, this is where you see something that I misremembered and somehow mixed up with the Young's modulus, which is the coefficient of volume expansion. It's defined the way that you'd expect it to be defined. Let's see, where do they talk about the actual definition of volume expansion? Yeah, the thermal expansion in 2 and 3 dimensions, and coefficient of volume expansion is this beta. And now, so this is where I remember. Yeah, it's about 3 times the linear coefficient. And you can see here, now it's not exact because, material properties are complicated. It's, 3 times 25, well, that is 75. But 3 times 19, that's not 56. That's, that's I think, 58. No, 57. That's 57, so it's 1 off. 17 times 3, okay, that's 51. 14, okay, the 12 times 3, 36. Okay, that's off by 1. I wonder which one has the greatest difference. This is one of those parts. 0.4 times 3 is 1.2, not 1. And one of the things that affects quartz would be its crystalline structure. And when you have some kind of crystal structure, then you can get what's called anisotropy, meaning which direction you look, it makes things change. So when something has a crystal structure, it could have a particular structure that depends on what dimensions you look. I think maybe, I don't know. I'm not a material scientist, but so this is where you have that vector of 3 relationship, and this comes from calculus. In fact, let me see. Since not your textbook, since this textbook refers to the exercise 1.60, let's go take a look. What that's all about. It says, show that the bulk coefficient of volume expansion is equal to 3 times the coefficient of linear expansion by calculating an infinitesimal change in the volume of a cube. Okay, so that's what I want you to kind of demonstrate, because it shows the power of calculus, kind of usefulness of calculus. So let me just quickly go through that. So this is what we have. Imagine that we have some object, a cube. Let's make it easy. We have can't do this right. Okay, we have a cube of length L on a side, and with the coefficient of the linear expansion, you can say, oh, so if I heat this thing up a little bit, the length of one side will change by a small amount, delta L. Or let me use the calculus notation, small infinitesimal amount, dl. So the kind of expanded cube would look like, okay, so this would expand to here. Now, in this dimension, it would expand a little bit as well. And finally, in the depth dimension, it will expand a little bit as well. So this is the expanded cube that you're dealing with. So what you have is, so when you calculate the volume of a cube is L cubed, and the reason for the name. The new volume, the expanded volume, would each side of the cube would have the length L plus dl. So this is going to be L plus dl cubed. That parenthesis closing is important. So you might look at it and think that doesn't look like there would be any simple relationship. And this is the wonder of calculus. Let me just do a simple thing here that doesn't really require calculus. You can just work out the algebra. You can take this expression and just expand out the thing. Now, I happen to have memorized something called binomial coefficients. It comes from this, I think it's called the Pascal's triangle. You might have seen something that looks like this. It comes from, this is the sum of these, this is the sum of these, and I can keep going. One of the really useful thing about something like a Pascal's triangle is it gives you the coefficient for when you have these two terms. There's a reason it's called the binomial coefficient, two terms by, and you raise it to some power. Then when it's a third power, so this is my 0th row, first row, second row, third row. This third row gives me the coefficient of the terms that are going to come up. So when I do this, by the way, you can do this by hand, which might take even shorter than me explaining this particular procedure. When you do that, you end up with these terms. You have L cubed term, you have the L squared times the DL term, you have L times dl squared term, plus you have dl cubed term. Those are the terms. Oh, but I should have left a space in front of them empty because that's where these coefficients come in. That 1 there is the coefficient for this first term. The 3 there is the coefficient for this term. And I've gone in a certain order. I went in the order of decreasing power for one of the two terms and increasing power for one of the other terms. So this term also has 3. And this term also has, has 1. So that's the expansion. Again, someone just looking at it wouldn't think, hey, I don't know, that doesn't look any simpler. It still looks very complicated to me. Now, this is the magic of calculus. This is the part where describing this as infinitesimal is important. What that means is this is a quantity much, much, much less than L, to the degree that it might be almost 0, but not quite 0. Again, that's the calculus limiting procedure. That's the conceptual work you have done in Math 3A that we lean on in our calculus-based physics. So the magic of calculus is that when you have these very small changes, and you have these terms, you have that small change raised to power 1, raised to power 2, and raised to power 3. These two terms here that's been raised to higher power of this very small number, it's like taking 0.1 and squaring it and taking the third power and so on. When you do that, 0.1 squared is a 0.01, and it gets smaller and smaller and smaller. So now we might call this an approximation without introducing calculus concepts. We could approximate this expression by saying, oh, these dl squared, dl cubed, they're going to be so small that we can ignore it. And, approximation is fine. The one challenge would be that, it's an approximation, so it has some error associated with it. The magic of calculus is one where this relationship is made precise in the limit where dl is much, much, much less than L. So in that limit where, dl over L going to 0, approaching 0, that's the limiting procedure, this relationship becomes exact. We can say, oh, my V prime, which I might describe as my original volume plus some change in volume, is equal to, it's not approximately equal to, but it is exactly equal to this quantity here, L cubed, plus this second term here, which has only the first order non-vanishing term of dl prime, plus 3l squared dl, no, that's not prime, dl. So this is the relationship you get, and that's where you get this factor of 3. Let me bring this home here. So this L cubed and V, they're the same quantity from here. So I can cancel those two out. So I have this, I have dv. So if you're just looking at, I have dv is equal to 3l squared dl. That doesn't look, I don't know, it doesn't look different, or it doesn't look simpler. I still have this L squared dl. So, okay, let me just play around with the expression a little bit. If we are getting to bulk coefficient of volume expansion, then we are getting at, we need some kind of unit-less fraction, volume change per volume. So on the left-hand side, I can do that. On the right-hand side, let me divide with the expression that's equal to volume, which is L cubed. So so now you see some simplifications here. So this cube, of the three, two of the factors will cancel with this. So now you have this. This is the fractional change in length. This is the fractional change in volume. And there was, something that was relating these through the coefficient of linear expansion. And now you have this factor of 3. That relationship again that I was confusingly expecting in the Young's modulus that we don't have, because so with the thermal expansion, it's I think material science wise a lot simpler, because you are just literally taking this and changing molecular spacing between the particles. But with the Young's modulus situation where you have stress and strain, then I can see that this kind of simple mathematical consideration might not necessarily apply. So I think I'm satisfied with just realizing that, the factor of 3 that I was remembering that applies to thermal expansion, it's not going to apply here. But this kind of the binomial coefficient, something that we call binomial expansion, binomial approximation, it's an important analytical technique. So I guess as long as I mention the word binomial approximation, I can kind of write out what that looks like. I guess in the form I usually write, if you have 1 plus some small number epsilon raised to power n, and right now, for the time being, I'm going to pretend that this n is an integer. Doesn't have to be. I don't think it even has to be a real number. So for an expression of this form, you can say it's approximately equal to 1 plus n times that small number. That's what you see with this factor of 3 expression. This 3 is coming from this 3 through the calculus things we do.